Hello everyone, welcome back to Bytes of CSE. So in this lecture, we will be talking about the breadth first search algorithm. Now in search algorithm, you will be given a search space, a starting node and generally a goal node. So in this case, this binary tree is a search space. So binary tree is a tree that has got two, where each node has two children. Now in every node we have got two pointers using which we will explore the search space. One is a pointer that points to the parent of a node and another pointer that points to the successors of the node or the children of the node. Say for example, the pointer to the successor of node number 1 will be 2 and 3 in this case, and parent node, since this node number 1 is the first node in the search space, it will be pointing to null. For node number 2, the parent node will be 1 and so on. Now in breadth first search, what we actually do is, whenever we get a node, say we are given the first node, that is node number 1, we will explore which are the successors of this node number 1, that is 2 and 3. After we have gone through all the successors that belong, the direct successors that belong to this node number 1, we will move on to the next level, that is the successors of node number 2 and node number 3. Or in other words, we can say that nodes of each level is expanded fully before we move on to the next level. Why we are saying this explicitly is that, see, your exploration could have been like, you have this node number 1, then you go through the list of nodes that are successors to this node, and in the list, say 2 is the first node that appears. Now you start exploring node number 2, that is the successors of node number 2. So your search space could have been like this. But instead, in breadth first search, what we do is that we explore a particular level fully before we move on with the next level. So let's see how it works. Now, this is the frontier list that contains all the nodes that has not yet been explored. So for now, when we start the search, we have only one node, that is node number 1. So next we will find that which are the successors of node number 1. So in this case, it's node number 2 and node number 3. So we put that in the frontier list, that is node number 2 and 3, and we move this node number 1 to this explored set, that is the set that contains all the node which has been expanded, as we call it, that is all the successors of this node has been found out. So we place this node number 1 to the explored set. Now the exploration of the nodes in breadth first search happens in the order of a queue. That is, in the frontier node, there are frontier list, there are two nodes, node number 2 and 3. Since 2 was first added to the list, so 2 will be the first node to be explored. So by exploration, as we know, that the successors of node 2 is found out, that is node number 4 and node number 5, and these two nodes will be added behind node number 3. That is because we will next be exploring node number 3. Now we take up node number 3, and we have two successors of node number 3, that is node number 6 and node number 7. So these are added to the frontier after 4 and 5, and 3 is moved on to the explored set. The next node to be explored is node number 4, and the successors of node number 4 are 8 and 9. So we add these two nodes in the explored list, in the frontier list, and we put node number 4 to the explored list. The next node to be explored is node number 5, and the direct successors of node number 5 are 10 and 11. So 10 and 11 are placed in the frontier, and 5 is moved to the explored set. The next node to be explored is node number 6. So node number 6 has two successors, 12 and 13. So these are added to the frontier node, the frontier list, and node number 6 is moved to the explored set. So in this fashion, we keep on exploring. So the next node naturally will be node number 7 with the successors node number 14 and 15. And then we move on to the next level. It is node number 8, then node number 9. So this way, up to node number 28, the exploration path will be like this. At this level, all the nodes, as you can see, they don't have any successors. That is from node number 15 to 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27 and 28. They do not have successors. So what happens is that they are removed from the frontier and put to the explored set. So I highly recommend you to take a screenshot of this screen so you can understand how the nodes were explored from this frontier list. Okay, now moving on. Now we see that in this case, the search space was a binary tree, that is a tree where each node has two successors. So if we consider this level as node that is level number 0, this level as level number 1, this as level number 2, this is considered as level number 3, and this included, and this is the level number 4. So we can see at level number 0 we have one node. At level number 1 we have nodes 2 and 3, that is 2 nodes. At level number 2 we have 4 nodes, that is 4, 5, 6 and 7. At level number 3 we have 8 nodes, that is 8, 9, 10, 11, 12, 13, 14 and 15. And at node number at level number 4 we have 13 nodes. So this can be rephrased as 2, that is level number 1 contains 2 to the power 0 nodes. Level number 0 contains 2 to the power 0 nodes. Level number 1 contains 2 to the power 1 nodes. Level number 2 contains 2 to the power 2 nodes. Level number 3 contains 2 cube nodes. And well, 2 to the power 4 is equals to 16. Now since 14 has no successors and 15 is also a leaf node, that is a node without successors, so 3 more nodes could have been added had this been a complete binary tree. So at any cost, the number of, that is the maximum number of nodes at 4th level could have been 16, or you can say that this is 2 to the power 4 nodes. So at any level D, so as you can see, this is 2 to the power the level number, 2 to the power the level number 1. So you can consider this as the level number and this as how many children are in the node. So for a binary tree, the maximum number of nodes at level D is 2 to the power D. Now if we move on to some tree like this, say this has got B number of children at each level. So we can safely say that at each level the number of nodes will be B to the power D, where D stands for some level number. This is a finite integer, that is the level number. Okay. So in case of binary search, in case of breadth first search, at each level you need to explore the number of nodes in that level. So at each level the maximum number of nodes explored is B to the power D, and that gives the time and space complexity of a breadth first search. Now this is taken directly from the Stuart Russell book on artificial intelligence, which says that if there is a tree that has a branching factor of 10, that is each node contains 10 children, and the node generation rate, that is time taken to that is number of nodes generated per second, be 10 to the power 6, the storage requirement of each node be considered to be 10,000 bytes, then at depth 2, the time requirement or the time latency will be 11 milliseconds and the memory required will be 107 kilobytes. And as the depth increases, say at depth number 16, the number of nodes will be 10 to the power 16. As a result, the time to explore the nodes will be 350 years and the memory needed will be 10 exabytes. So for a very large tree, breadth first search is apparently not a very good search strategy. It takes up too much time and memory. Okay, now let us consider the advantages of breadth first search algorithm. Now we are taking the same search space as before, and say now instead of node number 12 we replace that with G1, and node number 16 has been replaced with G2, and each indicates that there is a goal. Now in a search space there might be more than one goal nodes. Say for example, if say you are to find out a chemist shop nearby, so you might have more than one chemist shops nearby, and whenever you reach to one chemist shop your search completes. So in this case, say this G1 and G2 be two chemist shops. Now the way breadth first search strategy works, now G1 is located at a level higher than G2. So naturally in breadth first search you will always be reaching node G1 before reaching node G2. So that says that the shallowest goal is always guaranteed in case of breadth first search. Now breadth first search, the second point says it's always complete. Why is it said that it's complete? Now see, let us take this node 1. Now node 1, in the list of the pointers to the directly connected nodes, we have two nodes, that is node number 2 and node number 3. So in this list, say we are exploring node number 1 and we are not doing a breadth first search. We might be doing another strategy where when we first encounter this node number 2, we start exploring node number 2 without even adding node number 3 in our list. And we explore this entire path, and this node and all the successors are have remained unexplored in this kind of a strategy. So this is kind of an incomplete search strategy because we don't know what are the nodes that are present at these levels. So a particular level is not fully explored before we move on to the next level. So that is what is meant by a complete search. So breadth first search is of course a complete search strategy. The third point says that it always gives the optimal solution provided the path cost is a non-decreasing function of depth. Now what does that mean? Say the cost of moving from node 1 to node 2 be 1, that from node 2 to node 4 be 1. That is the path cost of each like moving to the each successive level be 1, that is from 4 to 8 it's 1, and 8 to G2 it's 1. So the cost of moving from node number 1 to node number G2 will be 1 plus 1 plus 1 plus 1, that is 4. And let us consider this part, that is node number G1. So just like before, each path cost is 1, that is whenever we move to the next connected node the path cost will be 1. So the cost of moving from node 1 to node G1 will be 1 plus 1 plus 1, that is equals to 3. So of course, if this be the path cost, that is a non-decreasing path cost, that is the path cost to the next subsequent level is not lesser than the path cost of the previous level, then it will always give a better solution. Like lesser the cost, better the solution. But if we have a search strategy, say this path cost is 4, this path cost is 2, this path cost is, well, say 1, and this path cost is again 1. And we have something like this path cost is 5, this path cost is 4, this path cost is say 3, and so on. So the total cost to move from node number 1 to point G1 will be 5 plus 4, that is 9, plus 3, that is equals to 12 in this case. And in this case, this is also decreasing in a fashion. The cost of moving from point 1 to point G2 will be 4 plus 2, that is 6, plus 1 7, plus 1 8. So if like in order for the solution to be optimal, there like breadth-first generally provides an optimal solution, and that is of course dependent on the path cost. So if the path cost varies, like in this case this was the highest path cost, then it started decreasing, then there might be a case where breadth first search might not give you an optimal solution. So that is all about breadth first search. So that's all for today. If you have liked the video, please give me a thumbs up, and thanks for watching. Thank you.